Okay, so I want to have a look at the roots of a complex number. So by that I mean solving equations like z cubed is equal to -1 to find the value of z. And there's one obvious solution there, that's the real solution, which is -1. But we want to look for complex roots to this equation as well. And to do that I'll use the mod arg form of both z and -1. Now firstly I will let z equal r cos I sine theta. And that way I have z cubed, using de Moivre's theorem, as r cubed cos I sine 3 theta. Now -1 is quite easy to find the mod arg form, because if I plot it on an argand diagram, it's right here at -1, which has a modulus of 1 unit away from the origin and an argument of pi, 180 degrees. So -1 is going to be equal to 1 cos I sine pi. And so my equation then becomes z cubed, which is r cubed cos I sine 3 theta, equals -1, which is going to be 1 cos I sine pi. And so straight away I can equate the modulus. So by equating the modulus I get that r cubed is equal to 1, which tells me straight away that r is equal to 1. So back in my z up here, this is 1. Then I can say cos I sine of 3 theta must equal cos I sine of pi, which tells me then that cos 3 theta plus I sine 3 theta is equal to cos of pi plus I sine of pi. Just writing this out a little bit in a bit more expanded form. And then by equating the real parts, that's exactly what I do, equate the real parts, I get that cos of 3 theta is equal to cos of pi. Which tells me straight away that 3 theta must equal pi. But there's other options as well, and so 3 theta will equal pi plus a multiple of 2 pi. So I write that as 3 theta equals pi plus 2n pi, if you recall the general solution. Now what I want to do then is to get just theta. So I want to divide everything by 3 and get theta is equal to pi on 3 plus 2n pi on 3. And so now I can start to explore my solutions for z. I know now that the z is r cos I sine theta, r is 1, and theta is pi on 3 plus 2n pi on 3. So I just need different values of n. So I'll start off with n equals 0, and that'll give me that theta is equal to pi on 3. And so that'll give me that z, I'll call it z1, my first solution, will be equal to 1 cos I sine pi on 3. I could write that out as cos pi on 3 plus I sine pi on 3, which then lets me take it back to x plus iy form, and cos of pi on 3 is 1/2, and I sine pi on 3 is going to be I root 3 on 2. So there's one root, complex root of -1, cube root. I'll come back over and I'll go, well, when n is equal to 1, I'll get theta is equal to pi on 3 plus 2 pi on 3. In other words, theta is equal to pi. And so my second solution is cos I sine of pi. Again, expanding it out so I can write it in x plus iy form. And cos of pi would be equal to -1, sine of pi would be 0. So this was the real solution that we already knew existed. And it came about when n equals 1. I can substitute in n equals 2, and then I'll get theta is equal to, putting n equals 2, 5 pi on 3. Another way of looking at 5 pi on 3, it's in the fourth quadrant. It would be -pi on 3 as the principal argument. So that gives me z3 is equal to cos I sine of -pi on 3. And again, if I write that in x plus iy form, I get cos of negative pi on 3. That's positive 1/2. And sine of negative pi on 3 is going to be negative, and it's going to be I root 3 on 2. So I get this as my third solution to the cube roots of negative 1. Now if I continue with other values of n, what I would find would happen would be I'd just come back to a repetition of these 3 different roots. So I know that when it's z cubed, I'm going to have 3 distinct solutions. Once I've substituted my values of n and got those 3 solutions, I can now stop and say these are the complex cube roots of negative 1. What comes next is we should graph these roots, have a look at where they lie on the Argand diagram, and try and find some patterns to make this whole process a little bit easier.